I feel after the 3-minute blast we just saw, I feel really fortunate to have a whole 20 minutes here. And I feel like the first thing I should do is to rip up this white tape that they told us to stand between and free all the speakers that come after me. So I'm going to talk about, let me go forward here. Am I live? Whoops. Hey, okay. Let's see. The title was one that ILP created for me, but it's close enough. Close enough to the topic. How am I? Is that going to keep going? All right. So very quickly, I wanted to first say that I run a research lab. We have about 20 researchers, and we have 10 or 12 projects, and almost all of them are on batteries. So I want to tell you a little bit about things that we do that don't actually, aren't at a point where you might think of them as, incipient technologies. So, for instance, we study basic phenomena. What happens to phase transitions in battery materials. In the middle top there is NCA. This is the cathode material in the Tesla cars. And for instance, in this case, we can observe that at 4.5 volts, the particles start to fracture. They actually make noise. You can listen to them. Your batteries talk to you if you listen closely. And it tells you about failure modes. So these are really, and on the right, a great deal of interest currently in solid state batteries. We're trying to figure out if solid electrolytes that you've probably been hearing about will actually make it. They have some fundamental flaws. At the bottom in the center, we use magnetic alignment to try to develop new processes for making high rate battery electrodes. Lower right is a interesting flow battery. We call this an hourglass design. And as soon as you say hourglass, everybody kind of gets it. You can charge and discharge by tipping it over. So these are some things that we do that aren't quite, let's say, either fundamentally focused or aren't ready for prime time. The main thing I want to address today, I want to give you two examples of costs and what we expect to do about battery costs. And so I get asked a lot, and many people want to know, lithium-ion technology, how low can cost be? How low can battery costs ever be? And so there are two figures here. One is an academic study. That's the one on the left. And all it did was to collect other people's projections. So this appeared in a Nature journal. Right? Collecting other people's projections. And it shows that it asymptotically goes to about $150, $200 per kilowatt hour. On the right is one of the more widely reviewed and considered credible analysts. This is Avicen. And I want to point out to the rightmost bar that you see there, if you can read it, what it shows you is the breakdown of costs in lithium-ion technology. And this is projecting out the year 2025. And so one of the things you see here is that materials, the active materials is about 1/3, and then the inactive materials is another 1/3, and the manufacturing cost is another 1/3. Right? And so when we look at this cost breakdown, you can ask, what is it that we want to improve? Right? Okay, another way of looking at the cost, ground up, so bottom-up analysis. Right? We can look at the elements that are used in creating energy storage, cathode and anode. Right? And so this is a plot that has on a log scale on the vertical axis energy cost per kilowatt hour by the element. Right? Well, we've been trying to compile this kind of data for some time, and this doesn't actually tell you that much. Right? If you look at the elemental cost. This is a more interesting plot. Right. This one, I've shown beta versions of this. You may have seen me present something like this before. But what this takes, we call it the chemical cost of stored energy. That's the cathode, anode, and electrolyte. Because without those three components, you don't have a battery. Right? Everything else you can try to do something about, but cathode, anode, and electrolyte. And then we divide it by the stored energy. And so again, vertical scale is a log scale. And now this is the last 60 years. And if you look at the far right, far left rather, we actually go back 100 years. So this is the last century of batteries. Right? And so you'll notice that over the last 60 years, there's a grouping that is positive on this log scale. Right? And that's kind of crazy. Right? So that as time has gone on, we've created new battery chemistries that systematically get more and more expensive. Right? And so why is this? Right? And so this has to do with the pursuit of energy density. And I've actually gotten brave enough now to submit this in a publication. And so this may be published. Some of my friends, for instance, if the reviewer happens to be one of my friends who developed one of these expensive chemistries, we're going to get rejected. I mean, you may never see it in print, right? But we're going to try. There's a large spreadsheet behind this, so anyone, it'll be available data. You can scrutinize our assumptions and pick at them all you want, right? But this is what's been happening, and so. Well, there's a couple lessons here, which is, in the second part of what I'll talk to you about, is how do we really get costs way, way down on this curve? And then this pointer won't show up on the screen, but if you focus on the blue triangles, that's lithium ion, right? And a way to use this plot is to say, lithium ion, where's the cost today for just the energy storing materials? And it actually goes from about $35 a kilowatt hour up to about $100 a kilowatt hour. And so if you want to build a battery with a system level cost of $100 a kilowatt hour, which is a round number that many people use, you can look at this and say, what is the headroom you have above the energy storing cost to do everything else you need to produce a battery? Right? And so from this perspective, low cost lithium ion is there. And I'm going to talk to you about that because that's what 24M has tried to do, right? How to minimize, to use lithium ion chemistry, but minimize the added cost. If you've noticed sodium sulfur, it's down around $1 a kilowatt hour, and you might say, why doesn't everybody work on sodium sulfur? Well, unfortunately, this is just the chemical cost. And the irony is that sodium sulfur is one of the most expensive grid storage chemistries we have today, about $800 a kilowatt hour, right? So you do have to pay attention to the rest of the story as well, right? Okay, so lithium ion, my view on lithium ion technology is that the manufacturing method and the approach has been fundamentally flawed for its entire existence, now 26 years. Right? And the basic reason for this is that if you look at the world of industrialized products, are there any other examples of a volume product that's composed of thin films entirely? Right? And so lithium-ion batteries in a millimeter of stack are 25 layers. Right? So it's fundamentally a thin film technology that we've tried to build up into a bulk product. And so I'll ask, does anyone know of a similar example in the world of commercial products? Right? Capacitor. Well, that's another energy storage that has the same fault. Right? So usually something comes back like food. Right? Okay, so baklava being an example. Right? Okay. Wiener torte. So this is a fundamental problem, and this is fundamentally what we've tried to solve. This is the story behind 24M. Right? And so earlier, Joe Adaletta already gave you an intro, so I'm going to go through this very quickly. If you come to our facility in Cambridge, what we'd like to do is to actually let people feel and hold the electrode form, which is the key invention behind it. Right? And this is, what you'll feel is that this feels like a wet rag in your hand. And it has a thickness about, in this case, it's still not completely bulk, it's about a half a millimeter, but it's not 50 microns. Right, so it's 10 times thicker than existing electrodes. So at least we're moving in the range of much thicker electrodes, which is what the cross-section on the left shows. And so there's a number of products here that 24M has now created. And the large cell you see here is a 110 amp hour grid cell with 3,000 cycle life. We can build versions that have over 10,000 cycle life at slightly higher added cost. But this is kind of where the technology is going. And the idea here is that you've heard earlier about a little bit about new higher energy density chemistries. The lithium-ion roadmap looks something like this. The vertical axis is energy density, watt hours per liter. And coming along with varying degrees of probability of success are systematically higher energy densities. I don't want to spend a lot of time on this plot, but for instance, the red bubble there is lithium metal with a high capacity cathode, which a couple of the companies that you heard about earlier are focused on. So all of these approaches can be used in the 24M manufacturing approach. Right? We are not a single chemistry. We want to take advantage of everything that comes along. And if I can play this video, I'm not sure I can do it from here. I'm going to use up a whole 1 minute of my time. There it is. So in the center, what you see, that rectangular gray stripe, gray patch is an electrode that has been formed, right? And now what you'll see is you can tell that it's an anode because of the copper. It's being scanned for a metrology step. And now you'll see a separator laid on top of that, right? And you'll see that this is an electrode that from the very beginning is wet and is never dried. So one of the reasons the process is so compact, efficient, is that there's never a drying step. You see it wetting through with electrolyte right there. And now this will be mated with a cathode that's been produced on the other side of the machine. This is an automated line. And now you have a 1 amp hour cell. About 3 of these would be equivalent to your smartphone battery today. Right? And so that took just under a minute. Now, if you've ever seen a lithium-ion battery manufacturing operation, to create a cell is usually a multi-day process. Right? It takes 5 days or more before you actually get something back to test. What you saw here is something that the mixing took minutes before this video, and so the whole process really, this is a 1 minute process for making batteries. And so this is one of the reasons why we think that this is the way that it always should have been done in the lithium-ion world. If you were to roll back the clock a quarter century and say, knowing what we know about lithium-ion batteries today, how would you make a lithium-ion battery? It should look something like this. Right? Okay, let me change tracks, and I have roughly 8 minutes left. And I really want to talk about a longer-term view of what will happen when renewable generation, because of its dropping cost, starts to become a larger and larger percentage of the generation mix. Things like you already see in Germany today, right? Overcapacity of PV. California is on its way to doing the same thing. Right? And so I think the great news about the dropping cost of renewable generation is that it really leaves room in that pie for storage. Right? But what kind of storage will we need? Right? What I'm going to tell you about next is a chemistry which now on this map that I showed you earlier falls way down at the bottom. Right? And what we learned from the sodium-sulfur story is that sodium and sulfur are a very low-cost combination, but as a high-temperature battery is way too expensive. So a ambient temperature sodium sulfur could be a really low cost solution. That's what we've actually tried to develop, right? And so this is something, you see the terminology there, air breathing polysulfide batteries. So I'm going to try to explain what this is. And this is based on the fact that if you take sulfur, sulfur is unique in the world of electroactive materials. The cost of sulfur, which is very weakly positive, and in some places actually negative, right? But divided by the charge that it'll store, it has the lowest cost per stored charge of any electroactive material that we know of, except for water and air. Right? And water and air can be electroactive. And so the battery I'm going to tell you about combines sulfur with water and with air. Right? And so this is why the chemical cost is down around $1 a kilowatt hour. Right? And so the sulfur, most of you know, is widely available. And just as an example, pumped hydroelectric storage, the largest form of storage today at scale, this is a roughly 2 gigawatt facility, and there's roughly 21 gigawatts in the US today. On the right is a stockpile of sulfur in Alberta, Canada from the tar sands, 4 million cubic meters. And this is, if this were converted into lithium sulfur batteries, this would be 10 times today's pumped hydro capacity. Right? So there's a lot of sulfur that we can use here. And so I'm a professor, so I'm going to make you listen to a little electrochemistry for a minute, right? Because I have to explain how this battery works. Right? It uses sulfur and air, but it's not a sulfur-air battery because the sulfur never actually directly reacts with the air. Right? It's a long story how we arrived at this chemistry. But what it has on the negative electrode side is an aqueous solution of polysulfides, sodium sulfides or lithium sulfides. The lithium or sodium is the working ion, but when it crosses over to the left, the cathode side, it doesn't actually react with anything. What it does is to create a charge imbalance, which is corrected by either uptake or release of oxygen, depending on whether you're charging or discharging. So the sodium ion on the right-hand side behaves in the usual way as a redox couple. On the left-hand side, it disturbs the water equilibrium, and that's why it's air breathing. Right? And so this is why the components can be a very low cost. We have the sulfur, and we have some additional acid and base, and we add the sodium lithium through, in this case, sulfates, which are very low-cost materials. Right? So this is how this works, and where we are in terms of scale is a lab-scale prototype, but this lab-scale prototype has run for roughly 1,000 hours, and what we've learned so far is that the chemistry is very stable as long as we run it within the right range. If we try to expand the range of sulfur speciation too much, the cycle life decreases. But if we remain through the right range, at least at this point, 1,000 hours or more. Right? The catholyte is also very stable. What does the cost look like at a system level for this? Right? So the chemistry is very low cost, but this type of battery is going to be used in a flow battery construction. And so between pumped hydro, flow batteries, and underground compressed air, there are a lot of similarities. The power cost is the cost of either a turbine or of an electrochemical stack. So there's a certain cost of power. Then there's a certain cost of energy, which is in one case, either air or water, or in our case, very low-cost sulfur solutions. Right? And so it turns out that our approach, like compressed air, like pumped hydro, the cost of containing the energy storage materials, the tank, is actually more expensive than the fluids within. Right? That's an interesting thing. That is not true for other batteries. Right? And so the way that we can display this, and this I think will be probably my last slide here, is that if we think about the installed cost of storage, and the lowest cost storage we have right now is pumped hydro, electric, or underground compressed air, and those are all the symbols that you see. Those are all real data, right? Publicly available data for installed pumped hydro and on its way to being installed compressed air. The horizontal axis is actually the duration. And the reason this comes out as a natural variable is because if you have very low cost energy, but you have a higher cost of power, right, the longer the duration you run the battery for, the lower the system level cost, because the less stack you need, the less turbine you need. Right? So that's why these curves look like this. And the main point on this is that compared to other battery chemistries that we know of, we think that this is really the first one that can compete on a cost basis with compressed air with pumped hydroelectric storage. And we think it's highly scalable because of the abundance of sulfur. Right? Now, all we have to do, where we are in the technology development, is getting the cost of those stacks down. And that's where our main focus is today. If we can reduce the stack cost, we can compete. However, keep in mind that this is going to be a battery that has, compared to these other pumped hydro and compressed air, 500 to 1,000 times the energy density. Right? It's higher than lead acid, for example. It's less than lithium ion, but higher than lead acid. And this would be a technology that you can deploy either at reasonably small scale or at large scale. And so that overcomes a lot of the issues, geographical and environmental, that have kept, for instance, pumped hydro from being deployed more widely in the United States. Right? So I think I'm out of time. I'm going to stop there. I'll let you read the conclusions, but this is what we've been up to. And if we have time, I'd be happy to answer some questions. Thank you.